work with amazing collaborators and my postdoc, Tian, who's sitting there, and other students. Yeah, none of the work I'll be talking about today would be possible without them. So I guess we all like distributed setups, and so this can be a typical setup where you can just have some clients, some workers, and there's a central server there. It can be either physical or virtual, right? And then at a high level, conceptually, our objective is to learn some shared knowledge denoted as W. And so W can be model parameters, but it can also be something else, as I'll describe later in this talk, that can first serve existing clients well, and then second, generalize to future and similar clients, hopefully. So at each communication around T, so assume that we are using some iterative methods, which is usually what happens. Some information transmitted, and then some clients do some local work and send some updated information back to the server, right? And then server use some function to aggregate those deltas, the updated information, and then get the new kind of shared knowledge at the next round. And then finally, we just output W. So in this talk, I'm going to talk about different forms of heterogeneity. In particular, the first is heterogeneous gradients or model updates. So that can be caused by different distributions of data across the clients. Can also be caused by various systems conditions. And some clients may update very new updates. Some clients may update very stale updates. So they are different. And one specific challenge that I'm going to look at in this heterogeneous gradient setup is the heavy-tailed stochastic gradient noise. I guess some of you here are already here have heard of this heavy-tailed additional property of some of the model architectures. And then the second part, I would be talking about heterogeneous semantics. So you can imagine that these clients may be solving completely different problems, but with some shared underlying principles. For instance, some clients may be solving a high school math problem, and some clients may be solving undergrad level math problems. And there are lots of insights and underlying techniques can be transferred across those clients, but then maybe we cannot directly using gradient-based methods to solve them. And the current inference framework can be inefficient, and usually they always happens in isolation. So in particular, the first part is about optimization, and the second part is about distributed inference. Okay, so let's first look at the heterogeneous gradients. You're very familiar with this finite, minimizing this finite sum of the errors, this objective function. And here we can think of this WT as the model parameters, and each client will do some local updates to minimize the local functions on their local data, right? And here we have some inner optimizer to solve the local objectives for each client. And then we have an outer optimizer to aggregate those deltas and then finally aggregate them into the current global model WT. And then some new global model WT plus 1 will be formed. Right? So this is kind of a very typical nested optimization framework with both inner and outer optimizers. I think one of the most early representative method under this framework is the Fed average, which is very popular for federated optimization. And yeah, just briefly talk about this. And one popular way to hide communication is to do some local updates. And so here, each client I will accumulate the gradients locally and send the local updates delta Ti back to the server. What are the challenges here that we're going to look at today? The one is the gradient noise can be heavy-tailed, and that's empirically observed by many previous works, especially for attention-based models like transformers. And in one of the early papers, for example, if we just use ResNet to train some image classification task, the noise norm is distributed in a sort of symmetric way. But then if we use this attention-based BERT model, we can see that the gradient noise is distributed in, there's some heavy tails instead of following some light tailed distribution. And this can create some challenges for optimization. And the second challenge that we look at in this setup is actually the adaptive optimizers. Yeah?
A question on the last slide. I just want to make sure I understand. The histogram,
Yeah.
This is over users, or this is over distributed entities? What's the density over?
Oh, so here it's, in this paper, these plots are actually focusing on the centralized setup. So it's basically, we have a bunch of like data points just where the server has access to. It's not distributed across users. Okay. So this gradient norm is just across samples.
Oh, I see. Okay. So,
yeah.
So density here is examples.
Yeah.
Okay,
Yeah. So this general heavy tail noise issue exists in just optimization in general, and also exists in the distributed setup. Yeah.
Sorry.
Yeah. And another challenge is that adaptive optimizers can be costly in terms of the additional storage and compute like overhead to maintain those gradient statistics. For instance, for Atom, we maintain this like a cumulative sum of the gradients across different iterations, and for IMS-prop, we maintain the like the variance of the gradients. And I guess it's also the same for Atom, W, some other methods. And our insight here is that these two challenges can be inherently related, because we can view preconditioning as a way of doing soft clipping, and the clipping-based methods are known to kind of mitigate the issues of heavy-tailed noise, because intuitively we can just sort of like performing clipping as a way of just constraining the scale of the like gradients or model updates, right? But then still the challenge is that some of the clipping-based methods, they cannot adapt to the underlying geometry as the adaptive methods do. And the current adaptive methods, we need additional systems cost to maintain those preconditioners. So what we proposed here is to do the corner-wise clipping from both above and below to achieve the benefits of both, like to handle the heavy tail noise, at the same time also bringing some benefits of adaptivity without the additional cost of maintaining the gradient statistics. And we call it bi-clip because it's clipping from both, or scaling from both directions. So intuitively, what we are doing here is, so we can think of this as a gradient vector, and some of the values are positive, some of the values are negative. And after doing bi-clip, we clip the large coordinates. We keep the signs of each coordinate of the gradient, and we scale the large values to be smaller than some threshold. On the other hand, we also scale some of the small gradients to be larger because we have a lower clipping threshold. So after applying bi-clip, this is what our gradients look like. And our intuition here is that we're trying to approximate what those adaptive optimizers do. Is that some of the gradients, they may be small, but they're very informative. So in adaptive methods like Atom, maybe those coordinates will be like magnified. And here we are just using a like lower clipping threshold to scale those small gradients to be larger. And then on the other hand, the large gradients will be clipped to be smaller values. So this allows us to reason about convergence under heavy-tailed noise. Because it's approximating those adaptive methods, we are kind of like sort of using an effective larger learning rate for the informative but small coordinates of the gradients, and using a smaller, effective, smaller learning rate for those noisy but very large coordinates of the gradients. We can have some benefits of adaptivity, but we don't have additional memory costs as Atom or IMS-prop. Basically, the memory cost is the same as SGD, but the actual cost is the two scalar thresholds that we use to clip the gradients. In terms of the benefits in federated optimization, we don't need to maintain those heterogeneous preconditioners across the clients. So if you think about how do we incorporate adaptivity into the federated optimization pipeline, is that clients may have some local preconditioners, and then the server may maintain some global preconditioners. It's kind of not straightforward to come up with some efficient frameworks to kind of incorporate both local and global adaptivity, because you still need to transmit some of the intermediate, like preconditioners from different clients, in addition to their model updates or gradients. Right? And then because the clients may have different distributions of the data, we may need some additional techniques to maintain those heterogeneous gradient statistics across the clients. But if we're just simply doing this clipping, assuming that the preconditioners can tolerate some amount of like noise across different clients, right? We don't have to create a very fine-grained preconditioners. Then we don't need to maintain the heterogeneous preconditioners. And the formal definitions here is just writing it in slightly different form. So we maintain the signs of here. Oh, some slight switch of notations. We're using x instead of w to denote the model parameters, and xj is the jth coordinate of the gradient. So the input x is the gradient, and then we are maintaining the signs of the gradient. But and here d is the indicator function. So it is saying that if the absolute value of this coordinate is greater than our upper clipping threshold, we just clip it to be u. But if it's smaller than our lower clipping threshold d, we rescale that to be d. Just increase it slightly. Yeah, you can think of this as a general framework because we can use the idea of bi-clip at both inner and outer optimizers in this distributed setup. So here we have bi-clip at each local updating step on the client, and we have bi-clip on the server side. Here we're approximating preconditioning both locally and globally. Our analysis generalizes beyond the instantiations using bi-clip both at the local and global side. At the global side, we can use bi-clip. We can also use L2 clip, which is probably more popular forms of clipping that people often use in practice. It's just clip the gradients to some fixed L2 norm. And locally, we also have different other optimizers. So here's our analysis of tail opt. The idea is that basically to handle this heavy tail noise and this bi-clipping, our idea is that we need to schedule the clipping thresholds in certain ways such that the gradients are asymptotically unbiased. Otherwise, there's an additional challenge that we have to deal with, like the biased gradients after clipping. Right? But here we just assume that those clipping thresholds are also dynamically changing, so the analysis can go through. But in practice, in our experiments, we just tune some fixed clipping thresholds. And this is our heavy-tailed stochastic gradient definition. The alpha moment of the stochastic gradient is bounded for alpha between 1 and 2, and not including 2. So this allows for the gradient variance to be unbounded, which is another difference from prior works. And this is our result for the instantiation where we have server-side arm as prop and client-side either bi-clip or just normal L2 clipping. And in the possibly non-convex case, the gradient norm is upper bounded by t to the power of 1 minus alpha over 2 alpha. And this is the result of bi-squared clip. So bi-squared clip is using that two bi-directional clipping at both server and client side. And here's the convergence result. I think this is slightly worse than the first one, but in practice, this works better. I think that's another open question we're trying to look at. And another comment here is that because we're scheduling the clipping thresholds in our experiments, in our analysis, that may also help to explain why we need learning rate warm-ups in lots of the more than LLM pre-training or continued fine-tuning or fine-tuning stages. Basically, learning rate warm-up says that we need to start from a small learning rate and then gradually increase the learning rate to prevent instability and sometimes catastrophic forgetting. And I think that has natural connections with our clipping threshold scheduling, because effectively we are also doing some sort of learning rate warm-up in the initial stage. But then if we have Atom on the server side, then we're not able to get the same convergence rate as those two instantiations. So another open question. Yeah, so we have some empirical results on both synthetic and real data. Here on synthetic data, like the first optimizer is the local optimizer, and the second one after the dash is the local optimizer. We see that everything basically converges very nicely when the noise is light-tailed, okay, in the left figure there. But in the right figure, if we simulate some heavy-tailed noise and inject that into the optimization process, we see that, for example, average SGD doesn't converge. But then this red curve, which is using Atom on the server side and bi-clip on the client side, converges very well. And even better than Atom squared, which is using Atom both on the client and server side. And then the results on some real-world data sets. One is the transformer encoder task. This is a like kind of standard sort of small-scale glue benchmark, where we see that just by changing this inner optimizer from Atom to bi-clip, and then we keep the outer optimizer to be just fat average, we can maintain the benefits of adaptive optimizers like Atom, because we can get almost the same like final average performance. And then we did tune every hyperparameter very, very extensively, and then the detailed protocol is in the full paper. And here we also compare with one of the popular methods, dilocal, that is proposed recently, and we see that it's also very competitive, and at least on this data set, seems it has some like small improvement over dilocal as well. But then the good thing is that it's very efficient. We don't maintain any additional gradient statistics, and also it has competitive performance on generative models on the machine translation task. So this bi-clip optimizer itself can also be very useful in centralized settings beyond federated optimization. We also tested on just centralized learning, right? One on the CFAR 100 dataset with a vision transformer, and the other is on the squad data with Quen 2.5. We see that SGD is just bad on both of these tasks, especially this text data. And then bi-clip is as good as Atom on this, in these scenarios. But of course, it's not clear if we scale up things to like pre-training a multi-billion model even larger than that, what the performance would be. Right? That's also one of the interesting future directions. So this tells us that bi-clip is a principled approach to addressing heavy-tailed noise and heterogeneous preconditioners. On some tasks, it can achieve Atom-like performance with only SGD-like memory. Okay. And next, I'm going to talk about the heterogeneous gradients created by varying the system's conditions, where I'm going to talk about some of the asynchronous frameworks that we developed under heavy-tailed noise. So first of all, we consider two asynchronous modes. One, we call it server-centric and client-centric. So basically, server-centric is server is the first-class citizen, and clients just wait until the server broadcasts the model updates to them. And here we have an asynchronous buffer size of m. In the most extreme case, you can sort of think of m as 1, right? So if there are many, many stragglers in the system, the server does not want to wait at all, so the server just aggregates the model updates immediately once it gets any new update from any of the clients. But here we just assume that the server updates the global model whenever it receives m updates. So I think this challenge of asynchrony, or the need of asynchrony, is exists both in federated optimization, also in the more larger scale multi-data center training. For instance, if we have different kind of hardware capabilities of the different machines. So in addition to buying more GPUs, it allows us, it basically gives us another dimension of scale things up, right? And this is just a visualization of the server-centric mode, and the client-centric mode is just the server. Again, server updates the global model whenever it receives M updates, and clients support the latest model whenever it is free. So our first step in understanding this problem is to try to understand clipping-based methods. For example, bi-clip. How does it interact with asynchronous updates? So interestingly, so this is our empirical result, and we find that clipping methods maybe they're originally designed to improve the optimization process, to stabilize the gradient updates, to handle heavy tail noise. You can also mitigate the noisy updates coming from asynchronous training, improve asynchronous training as well. Here we see, the left figure is epoch versus the test loss, and the right figure is runtime versus the test loss. And we see that if we do asynchronous aggregation on the server side, but client side we use the bi-clip optimizer. In synchronous settings, it should converge. But because here we have asynchrony, which means that some clients will just send some very stale model updates to the server to be aggregated into the current global model. And so under extreme staleness, even one single stale update can be very detrimental to the current global model. It doesn't converge compare with this synchronous setting plus bi-clip. But we see that if we change the server-side optimizer to bi-clip, it can converge very well in the asynchronous setup, which tells us that clipping-based methods not only have benefits for dealing with heavy tail noise, but also have inherent benefits of dealing with asynchronous and noisy updates. We also have some convergence analysis, which I think is very similar to the previous analysis in terms of the techniques and the results. Here we have an additional assumption of the bounded delay or the bounded staleness, which we denote as tau here. But so we didn't include the dependence on tau in the upper bounds here, but basically we need to assume that tau is bounded and the dependence is O of tau here. And here, this dependence on tau is not very ideal because it just tells us that the convergence will be worse if we have slower clients. And if some clients are extremely slow, then it may not converge. And our next step is to improve dependence on the amount of staleness. Now, idea is actually quite natural. It's to just use a smaller server-side learning rates for more stale model updates. And I think some of the previous asynchronous optimization works have also studied similar ideas, except that just here we are doing it in a slightly different way and having a better dependence on the staleness. So this is what people do in the vanilla case. Is just they average these model updates to get the global model update delta t, and then they can just plug in this delta t into any global optimizer. And what we proposed is to divide this delta ti from the ith client by a client-specific staleness parameter, pti. So where pti is the gap between the current timestamp t and the timestamp that the global model, this client I, starts to optimize from. So suppose this client I, it fetches the global model x tau ti at this tau ti's round, right? And then starts to do optimization and do some work. And then finally, this client i's update is incorporated into the global model xt. And the amount of staleness that we have is t minus tau ti for this client I at the, for the teeth global model. Right? And the intuition is just that if those updates are very stale, we kind of downplay it slightly. And we observe that it improves performance empirically and also helps to ease hyperparameter tuning in practice. Okay, and here are the results where we can, under that staleness aware aggregation, where we can tolerate a larger delay. But then our convergence for bi-squared clip is slightly worse in terms of convergence rates. Okay. So far, we have shown that both clipping and staleness aware aggregation can help to mitigate the, the potential limitations of heterogeneous gradients and model updates. It can improve the performance and also can have some other benefits, like making the entire system more efficient in terms of the system's costs. And next, I'm talking about something during the inference time, where the clients can solve different problems given some existing, let's say, foundation models, LLMs, agentic tools, with some shared underlying principles. So that's why we need to do some sort of federation, but slightly in a different way. One example is that all of the clients, or you can also call them agents, they have access to some LLMs, but they are solving different types of problems. Here, in this example, they're both solving math problems. But it's not limited to that. You can imagine that client A can solve a computer science problem, client B can solve a biology problem, right? And there are a ton of shared insights and techniques from different communities. And maybe just people previously have not realized that they're just solving their own problems using their own languages separately. But actually, there are lots of the insights that can be transferred across different domains, different communities as well. And in the current agentic reasoning frameworks, reasoning usually happens in isolation. Is that, for instance, in this example, when client 1 solves the math problem, it may not directly learn from the reasoning process that the client 2 has. And another drawback is that people usually do, or those agentic frameworks do reasoning from scratch without the guidance of the application-specific knowledge. So users just feeding current LLMs, like asking some questions, and then you would just output some answers. But then the reasoning traces that those LLMs have may be lost during cannot be efficiently reused during the process. So actually, federated learning inspires us to develop a federated inference framework to partially address those problems. In federated learning, we do gradient updates, but they can be very computationally expensive, and the gradient space may not be very interpretable and may not be suitable to share the abstract reasoning strategies. So in federated inference, or in the framework that I'm going to talk about, we propose to handle those heterogeneous semantics where all these operations are performed at the semantics level, not the gradients or model level.
Tian, is the goal here to actually update the model, like to take these reasoning traces and then to feed them back in via post-training, or is it to only modify what's happening at inference?
Oh, that's a good question. That's the second case. Okay. Only modifying what's happening in practice. Okay. So the models do not change at all. Yeah. So here the left part is federation over gradients, which is the common distributed federated learning setup that we're familiar with. And this right figure visualizes what we call federation over text. Just everything is done in the text space and no additional training or reinforcement learning based updates happening. And the goal here is to, different from federated learning where the goal is to output a global model, But also relatedly, the goal is to output some what we call the insight library that can be useful for those existing agents or clients to solve their problems and can also be useful for future agents that come into the network. And there's some interesting analogies that we can draw between these two frameworks. So in the first step, what we do is that, okay, so the server has some empty insight library, right, at the beginning, and then just broadcast the current insight libraries, which is a collection of the distilled, high-level, actionable, generalizable knowledge or insights that we learned from all those tasks so far to those agents. And then the agents will do some local reasoning, self-reflection, self-improvement. You can plug in any of your favorite reasoning methods to solve the local problem with the presence of this insight library. And then those agents will upload their reasoning traces, which can be some metacognitive summaries of what they're doing to solve their problems, to the server. And the server will aggregate those traces to further distill some shared insights and then update the insight library. And this process can happen iteratively. In our current framework, so everything happens in this natural text space. For instance, how do we do aggregation? There rich a space of design choices there, but we're currently doing is that we just basically do some prompt engineering. We just ask an LLM, okay, can you aggregate those different reasoning traces and update the library? But the actual prompt is much more complicated than that. But that's at a high level what we're doing, without any additional training or parameter updates.
Sorry, just to make this more concrete, would you be able to tie it to this initial example you gave where there were two clients and each one was solving a different math problem? So shall I think of these agents as these clients that have the math problems?
Yeah, I'm going to talk about this application right now.
Okay,
yeah.
Sorry.
So each agent, here we have 8 agents because we have 8 benchmarks of math problems. And each agent solves a math problem with certain difficulties. So I have AIME 24 and all the way to, so some simple math problems, some difficult math problems. And each agent basically uses an LLM together with the insight library that we generate in the system to solve those tasks, to answer those questions, basically. And then we measure because those are standard benchmarks, we can easily measure the accuracies of those math problems. And here, so what are our baselines? This single agent means that we are just trying to ask each client or each agent to directly use the LLM. Here it's DeepSeek, but I'll show results of Gemini later. To solve the task at hand, and then we compute the average performance across the 8 benchmarks, those 8 agents. And here, these two kind of dots, they are the results of our framework at different iterations. So we're showing that it has some improvement in terms of the average accuracy. And then the x-axis is the average number of generated tokens that we have in solving those problems. Analogous to the federated learning setting, you can view this as the average number of optimization steps that you need to solve the problem, right? If you have a global model and then start to do fine-tuning of the global model, as long as the global model is useful for your task, then hopefully the number of optimization steps will be significantly reduced compared with the number of steps if you just solve that from scratch. And here it shows that with our insight library, the average number of generated tokens is also greatly reduced compared with this baseline, which is to reason from scratch. So here every client is using the same DeepSeek model, but then this framework itself is really agnostic of any local reasoning model or local LLM that each agent uses. And this green dot, that is showing the performance of using DeepSeek to do local reasoning, but plugging the insight library that is generated by a more powerful model like Gemini. We can see that achieves the best performance with the least number of generated tokens. So here, this right figure shows the trade-off between accuracy and the total loops, because one kind of annoying thing that can happen in practice is during those reasoning process, we can have, basically the problem would just be stuck somewhere and keep generating the looped reasoning process. And we see that using our method, the total number of loops can also be reduced. And then this is the result using Gemini 3 Pro, where we see that can also improve the accuracy slightly. But we are still working on further optimizing this entire framework, having better prompts. And we also tested other applications. And it's still kind of early work in progress, and we're actively working on these directions. So we're thinking about basically discovering some insights for machine learning research, right? And then one kind of idea is to look at the machine learning papers in year X and then test if our generative insight library can cover or guide, there's some typos here, can just guide the future research by looking at machine learning papers in year X plus 1. And what we compare with is, okay, we directly ask LLM to release before year X plus 1 to generate the insights, because then we can make sure that those models, they have not read the papers that are published in year, hopefully papers published in X plus 1 year. And then the second baseline is we directly ask the LLM released after year X plus 1 to generate insights. And the second one can be stronger than the first one because we have a stronger model, and also the potentially the model have already seen those papers. And another baseline is that also instead of learning the insight library from in a federated way in the framework that we looked at before, we directly feed those papers generated in year X into a RAG system, basically treating those papers as raw data, raw text, and directly ask the LLM, okay, what insights you have given the existence of those papers. And then those are some of the early results we have. Gemini 3 Pro is released after year X plus 1, and Gemini 2 Flash is released before year X plus 1 in our test. So we see that. So first of all, we compare the first panel and the second panel. And this single agent baseline is basically we directly ask Gemini, okay, give me some machine learning ideas or machine learning insights directly based on different areas. And then we test if those insights can guide the papers in year X plus 1 for different Gemini models, for 2 different settings. And then the first, which is our method, is to obtain the insight library in the framework that we discussed before. And we see that Gemini 3 Pro probably have already seen those papers, and then so it can be so much better than Gemini 2.0 Flash. But then for the second Gemini Flash model, we see that compare our method with the single agent setting without any federation or collaboration, the percentage of papers that we can cover from the insight library can be much higher than in the single agent setting. And then we also compare, this is a stronger setting where we just feed in these papers into this RAG system. And we see that our framework can also have some slight improvement over these settings. Yeah. But then we're still working on it. And in the future, we are interested in other applications in the scientific domain and cross-domain discovery and more. Yeah, questions?
So what is the cardinality of federation here? What are, this federation over text, how many clients do you have? And what does each client represent? Are they they're fed different insights?
Yeah, different areas basically, because we just get papers from the iClear website where we can have meta information of the areas that these papers belong to. And then basically each client is responsible for one sub area.
Okay, so can you give just a rough sense of like how many clients, how many areas did you?
Yeah, I think we consider roughly like 20, 30, yeah.
I'm curious, this is always sort of, I guess, like a open question in this vein of like, when you have these sort of notions of experts, like, you know, do you do these sort of like atomic, monolithic LLM experts versus like mixture of experts where it gets much more kind of granular? I'm just curious how you kind of came to this approach versus like the mixture of experts where it's much more sort of, you know, baked in at a more fundamental level in the transformer. Yeah.
Yeah.
I'm always curious, like, what, you know, what motivates different positions in sort of the
Yeah.
mixing space.
Yeah, that's a good point. So I think in mixture of experts, we are kind of, like the goal there is to kind of determine or let the MOE system to automatically determine the routing like policies of the different inputs. Whereas here we try to learn a shared library that can just be used or plugged into any of the future reasoning processes as well. And I believe the Gemini models here, they are also using some of the like MOE architectures already. And also for MOE, I feel like it's not very interpretable in terms of like what experts learned, like what subspaces for that problem. So I think here in our case, if we just send the communicate the text and everything and to generate some global library or knowledge, that can be used as something that can basically augment the current learning system. Right, the LLM can use whatever architecture, like MOE, for example. But then we can just plug in this insight library as it's kind of like a pre-trained model in the federated optimization setting. And having access to that pre-trained model, you can use any optimization algorithm to further optimize that model. Is here having access to this shared library, we can use any model architecture like to further solve the reasoning tasks. Yeah, but I think it's also interesting to understand kind of what shared model or what shared knowledge that indeed that we have learned and how that compared with the knowledge that is learned by MOE. Yeah, but I think because we're focusing totally on inference, that's.
Yeah, I have a question, I guess, relates to the last thing you said. For the previous case where you were solving the math problems, and you get this improvement in accuracy, right, when you federate the insights at time of inference. So each of these clients is already using a model that's supposedly trained on all these data sets for math problems, right? So what is it that they learn at the inference time from the problems they're
That's a good question. So I think there can be two cases, two things happening here, or can be a mix of the two cases. One is that they're learning a better way to kind of retrieve the knowledge that is already installed in those models, right? So that you can improve the inference like performance on that specific task. So maybe the knowledge is already there. It's just this shared insights gives us a better way to like retrieve them.
Because you're probing it with two different queries maybe, and that's two different ways to.
Yeah, because we are getting those insights from many similar tasks, not a standalone task that can help improve. And then I think in this application, we're actually showing. Basically, in this setting, the model itself does not have access to the machine learning papers because the model is released before the papers are published. So I think here it also shows another possibility is that the insights themselves will learn something new, like in addition to the knowledge that is already stored in the model. Yeah, but I think it's interesting to kind of rigorously evaluate what happens, in the future.
Thanks, Tian.
Yeah, thank you.
All right, so we will be back. We have lunch now and a nice break for lunch. We'll be back at 1 for the afternoon session today.
Sure.